In this lecture, we'll use key concepts about circuits to analyze a particular circuit in detail. Analyze means that there will be some quantities describing the circuit that are unknown and that we'll need to figure out. First, though, let's discuss how to represent an energy source in a circuit more generally. Up to now, we've used a battery to represent this. However, there are other energy sources, like cell phone power adapters or solar cells, that aren't batteries. To account for this, we will use this symbol. Two parallel line segments, one longer than the other, the long line segment representing the plus terminal, and the short line segment representing the minus terminal for an energy source in a circuit. Everything else is just as it was before. For example, if we move in the direction shown by the arrow across the energy source, that is, move from the negative terminal to the positive terminal, the potential difference across the energy source is positive and equal to the EMF. Now let's analyze this circuit. We're given the EMF, it's 12 volts, and we're given also the resistances of all three resistors in this circuit. And we want to find out all of the currents that flow in this circuit. One way to start is to apply our circuit rules. We notice that we have multiple currents, so let's start with our node rule, which says I1 equals I2 plus I3 for the currents in this circuit. We can also apply our loop rule and do so multiple times because we have multiple loops that make up this circuit. For example, there is a circuit loop on the left. We're free to choose a direction. Here we are choosing to go clockwise around the loop. In this direction, the loop rule tells us that the EMF plus delta V across the resistor R1 plus delta V across the resistor R2 equal to 0. If we apply Ohm's law to the resistors, we end up with this expression. Let's choose another loop, say the loop on the right. And again, we can choose the direction as we like, and we'll choose to go counterclockwise around this loop. Here is the loop rule for this loop. Delta V across resistor 2 plus delta V across resistor 3 is equal to 0. And again, using Ohm's law, we end up with this expression. Now notice, we now have three equations that are shown in the boxes, one from the node rule and two from the loop rule applied to different loops. And we have three unknowns, the three currents. So we could solve for these algebraically. I encourage you to do this, where you do so symbolically and plug in the numbers only at the end. In the rest of this lecture, we're going to show how to solve this problem in a different way. But first, let me point out something. There is a third loop that we could have used, shown in green. This third loop provides no additional information, so we don't need to consider it. Let me just say this in another way, more generally. For a circuit with n loops, only n minus 1 are independent and therefore useful for solving for unknowns. In this particular case, any two of these three loops could be used. The third loop would just be redundant. Our alternative solution to find the currents begins by noticing that the resistors R2 and R3 are in parallel. So we could create a simpler equivalent circuit with an equivalent resistance, R parallel. We're using two vertical bars here to represent the concept of being in parallel. Here's how to determine R parallel from R2 and R3. Inserting the values for R2 and R3 and solving, we find that R parallel is 4.11 ohms in this case. Here's what the simpler equivalent circuit looks like. Notice it has only one current, I1. This should make it easier for us to solve for I1. We could do so, but let's make this circuit even simpler because we notice that the resistors R1 and R parallel are in series. So the equivalent resistance for this series combination is given by the sum of R1 and R parallel. Here's an even simpler equivalent circuit where we can now use the loop rule once and Ohm's law once to solve for I1, which is the same I1 in the original circuit, 2.35 amps. Let's now keep this result for I1 in mind and revisit our more complex versions of this circuit. Notice that I1 passes through the resistor R parallel, so the potential difference delta V parallel can be found using Ohm's law and our knowledge of I1 and R parallel. Here is the result. Now notice, across our resistors R2 and R3, the potential difference is also delta V parallel. So we can use Ohm's law on each of these original resistors in turn. First, to find the current I2, which is 1.61 amps, and then to find the current I3, which is 0.74 amps. Now, as a sanity check, we can test to see if the node rule is satisfied. Is I1 equal to I2 plus I3? We can do the math and see that this checks out. So this gives us confidence that we've solved for all the currents correctly in this problem. That's it for this lecture. In our next lecture, we'll talk about the electrical property of capacitance, which we'll use to characterize a different type of circuit element.